Good morning, and welcome to us live in San Francisco and online all around the world. My name is Stephen Oliver. I'm the VP for Corporate Marketing and Investor Relations at Navitas Semiconductor. Thank you for joining us today. This is an exciting stage in the growth of gallium nitride, or GaN, next generation semiconductor technology. The information discussed today is qualified in its entirety by the Form 8K filed with the SEC today and may be accessed on the SEC website and also via navitassemi.com. A video recording of today's presentation will be available shortly. Please review the disclaimers included in the filing. Statements made during this call that are not statements of historical facts or otherwise constitute forward-looking statements are subject to risk, uncertainty, and other factors that could cause our actual results to differ from historical results and or from our forecast. Do not place undue reliance on forward-looking statements, for which we assume no responsibility for updating. Let's meet the experienced team here today, starting with Navitas. Gene Sheridan, co-founder and CEO. Dan Kinzer, co-founder and COO CTO. Todd Glickman, our Senior Vice President of Finance, and Dave Carroll, Senior Vice President of Worldwide Sales. I'm also pleased to introduce Gary Wunderlich, President and CFO at Live Oak, who have made this company acceleration possible. Also here today are Laurie Barker and Graham Robertson from Blue Shirt and Grand Bridges. That's our IR and PR partnerships. Our presentation today will be followed by question and answer, and then by product demonstrations that will show the size, weight, and energy saving benefit of GaN power ICs. We will have a mobile camera so those online can follow along. During the question and answer, we will alternate from those in person and those online. Now, let's learn about gallium nitride in a short video, and then welcome Gene Sheridan, Navitas co-founder and CEO, to begin the main presentation. Thank you.
All right, good morning. Welcome, everybody. It's great to be here today, an actual in-person event for many of us. First time in almost 18 months, I think, for me, and maybe the same for you guys. So it's an exciting time for Navitas. But more importantly, I'd say it's an exciting time for the world of power electronics. We started the company 7 years ago with the goal of really revolutionizing the world of power semiconductors and power electronics, and starting with gallium nitride. I'd say we're off to a great start, and we're excited to show you that start today, including a lot of demos, samples, and prototypes, and give you some deeper insights that we haven't shared before. But we've got a long way to go, and we're going to talk about the roadmap to make it happen as well. So as a next-generation power semiconductor company, This gallium nitride power IC technology is pretty exciting in delivering up to 3 times smaller, lighter weight, faster charging power electronics, while at the same time delivering big energy savings up to 40% or more. Our GAN IC platform is already a market leader with over 20 million units shipped, not a single GAN-related field failure, which is really impressive and important in a very reliability-driven power electronics space. But I'm also pleased to announce for the first time, a few months ago, we announced, when we first announced our IPO, we had 75 GAN chargers in production. That number, as of today, has already jumped up to 135 GAN chargers in production. Nearly all of them you'll see in the demo later today. We combine that with over 120 patents issued and pending, we believe has created a multi-year, highly protected lead for Navitas. We think this puts us in a great position, not only in mobile chargers and adapters, where we're off to a great start, but to really tap into a $13 billion GaN electrification opportunity that goes far beyond chargers and adapters, but also into enterprise, which is mainly data centers, renewable, with a focus on solar, and electric vehicle and the broader e-mobility segments. On top of this great financial opportunity in converting that $13 billion from silicon to GaN, there's also a huge opportunity to help the planet. The net zero initiative by the Paris Accord for 2050 is a big challenge. It's one we take seriously, and we're super excited that we can have a big impact. Literally, with every GaN chip we ship, we save energy. Less energy means less CO2. By our estimates, that could be up to impacting 2.6 gigatons a year in reduced CO2 emissions. These are big numbers, ambitious numbers, but we're serious about it, and we're actually hiring third-party experts to help us audit it, set up the metrics, and drive the measurement and ultimately the achievement of these sorts of goals. Now, how are we going to do this? Why do I think we're quickly emerging as a newer company, 7 years old compared to many others? Why are we off to such a good start, I believe, and the early technology leader and market leader? In the end, it comes down to the team. And I think it's my great pleasure to work with people that I've worked with, many of them over decades in my career. These are the best of the best in power semiconductors, in power electronics, not just in years, not just in experience, but in actual value creation. Technology innovations are incredible, building new product lines, new businesses, and ultimately changing the face of power semiconductors and power electronics. And finally, visibility. All of this has come together to build a pretty exciting customer pipeline, primarily in chargers and adapters, but very quickly, just in the last 6 months, we've engaged new customers in our new expansion markets, and that's already added significantly to a total $680 million customer revenue pipeline. That's a huge pipeline, gives us a lot of confidence, gives us a lot of visibility to our revenue plan to nearly double our revenue over the next 5 or 6 years every year, but we also have significant capacity expansion. We'll talk to you about how GaN utilizes plentifully available silicon manufacturing tools that gives us a leg up in supporting short lead times and upside capacity to actually exceed the kind of revenue forecasts that we'll show you today. So first, a quick introduction. What is GaN? I think you know it, but to be clear, we're talking about GaN for power. You will find GaN used in other markets like opto-LED and RF. Here we're squarely focused on GaN for high voltage power supplies. Gallium and nitrogen combine together to create GaN, or gallium nitride, which is a very powerful bond, 10 times stronger electric fields compared to silicon, 2 times faster electron mobility. What does all that mean? It means you can produce a tiny chip that handles high voltage and high power that can switch very fast and very efficiently. And the vast majority of this market we're addressing are switching power supplies. Speed and efficiency is the name of the game. The faster you switch, the better the energy efficiency, the more you can dramatically improve power density, up to 3 times smaller, lighter weight, faster charging, higher power density, while still delivering that big energy savings, 40% or more, and ultimately it will be a cheaper way to build power supplies. So that's a quick introduction again, but it's my great pleasure to also introduce my co-founder, business partner, all-around great guy, and world technology leader second to none in power semiconductors, with well over 100 patents just to his name, Dan Kinzer, our COO and CTO.
Thank you, Gene. And it has been a great pleasure to work with you to build this company, and in times past when we had lots of other challenging, exciting power semiconductor projects together and great business successes. So I'd like to review with you why is GAN integration an important thing? Why is what Navitas has done so groundbreaking and so changing to the power electronics world? So starting at the bottom of this graphic, you can see basic silicon devices, a driver, a passive component, a couple of TO220 power packages, very standard in the industry. This is what people have been doing for many years. And those devices tend to operate at 100 kilohertz or below. At 100 kilohertz, you have to deliver a pretty big packet of energy when you are operating a switching power supply. And because of that, you have to store that energy in large magnetic transformers, inductors, and then large capacitors. And because the efficiency is only 85 to 90%, you have to take the heat away from the package and deliver it into the environment with big, heavy heat sinks or other thermal management devices. Let's call that 1x on size and weight. With discrete GAN, you can make some improvements. You can have more energy efficient packages, and you can run at higher frequencies, and you can get a little better efficiency overall. But you have to add a lot of extra components. You have to add a number of passives and external drivers, and you really have to watch out for overstressing the gate. Having done that, you now have a system that is a little higher frequency. The passive components have reduced in size somewhat, and now your heatsink can be a little bit smaller, and you've raised your energy efficiency. Let's call that 2x. With Navitas, with our integration technology, now you take all those extra devices, you put it inside the same chip, inside one package, and deliver a very compact solution that is protected, that is well driven, and that is very, very efficient. You can operate it up to 2 megahertz, and fundamentally, GAN can go much higher than that. It can go up to 20. But we don't normally do that because we don't have to in power supplies, and the passives may not be ready for that. So, but we can shrink those passives to be extremely small and lightweight, and essentially eliminate most of the thermal management because we're operating at such high efficiency, up to 95 or higher. So let's call that 3x. That's the way GAN improves power electronics. Let's dig a little more deeper into a specific application of mobile charging. So on the top level, you can see what a silicon discrete solution looks like. It's 145 cubic centimeters. The driver is separate from the power device, and in between the two, you have board-level parasitics, inductors and resistors. Those board-level parasitics slow down the device, and they also cause unwanted waveforms to be applied to the gate. However, at low frequency, silicon devices can handle that, and you get an efficiency in the high 80s. With GAN, there are two different types of GAN devices that have been available in the market, D mode and E mode. D mode devices is short for depletion mode, and those devices are normally on. E mode is enhancement mode, and it's a normally off device. You have to enhance the channel for it to turn on. So in the case of D mode, because it's normally on, you could short out the power supply as soon as you apply power to it. So you have to add a MOSFET to keep it off, an extra silicon device, which adds to the parasitics and the delays and adds to cost and complexity of the solution. Nevertheless, you can operate a little higher in frequency, as you may imagine, and a little higher in efficiency, and you get some shrink. With E mode, with discrete devices, you have a complex circuit that you need to add to control the E mode gate. You're now driving a transistor that is very sensitive, very fast. You have to protect the gate from overvoltage stresses, and you have to drive it most frequently with both a positive and a negative gate drive. That's complicated and adds cost and space. So again, you can get even higher in frequency and up to higher efficiencies. We've said, okay, about 40% shrink you can do with GaN discretes. But with GaN ICs, you can integrate all of those drive and protection functions and, again, switch very high in frequency. And now you can get that 3x or 65% shrink of the adapter. And we'll show you those in the room shortly. This is a typical comparison between a discrete GaN circuit. This is a so-called half-bridge circuit. It's got two discrete GaN devices and all of the driver components. They add up to 28 components to drive those two devices. And we have a GaN power IC, which has only 14 components and about half the components and about a third of the area of the PCB is taken up with the total solution. The biggest issue, though, besides the area and besides the number of components, is the waveform that you get out of that. So in the waveform that you're looking at there, on the left, this is the discrete one. The green curve shows the current ramping up with each pulse, applying more and more energy into the circuit. And as the current ramps up, you see overshoots and eventually you see oscillation. That's what happens because of the parasitics on the printed circuit board, losing control over the gate. In the right, you see the integrated device with perfect control over the gate, perfectly square waveforms, textbook style, ramping up the current with no issues. Because of these type of phenomenon, the gate being exposed to transients and the drain being exposed to transients, discrete devices can have limitations in their reliability in their lifetime. We have data that estimates that we have 100 times improved reliability compared to the discrete device and a very, very low failure rate, which is evidenced by the fact that we've shipped 20 million units and they're in the field and we have had no field returns. So we've spent the last several years overcoming the major hurdles of gallium nitride, and there have been hurdles, both in manufacturability and reliability. But having worked with, GaN is a very interesting material and a little bit difficult to grow because we're basically putting a thin layer of gallium nitride on a silicon substrate. That silicon substrate has a different lattice constant, which means the spacing between atoms is different than gallium nitride. It also has a different thermal expansion than gallium nitride. So when you grow a film on it, it has a tendency to warp or bow. These kinds of things and others have to be controlled in the manufacturing flow. And we've worked for years with our partner TSMC to develop a highly refined, highly manufacturable process and design, which has led now to stable 90% yields, 90+% yields that are similar to those that are achieved in silicon power devices, mature silicon power devices today. Those phenomenon that I described can also lead to low reliability with high defect densities if not properly controlled. But we have run many, many reliability evaluations and tests. We have over 1 billion equivalent device hours that we've put into testing. And as I said, 20 million units shipped, no failures. The other factor that we have addressed is the complexity of driving the device. We've basically integrated those extra system components into our chip. Now the user only has to deliver a low voltage DC input and a digital input signal. And we can take the rest of the way into a full power solution. Having done all that, getting those kinds of yields and manufacturability, and being the lead GaN producer in the market today with our volumes, we're able to get great pricing from our suppliers and drive the most aggressive GaN manufacturing cost scenario in the market. So that leads into this slide, which we have the early mover advantage. We have low manufacturing costs due to our volume. We have the high yields to support a low-cost structure. In addition to that, we're developing a new generation every year. which will deliver performance improvements in the range of 20%, die size reductions, and we're adding new levels of integration every year, putting in more functions into the product, which will protect the device, control it, and improve its efficiency. All in all, we expect to get higher frequency every year, lower the magnetics and capacitive element sizes around the device, lower the overall system cost, and our system costs within the next 1 to 2 years should cross over that of silicon solutions today. With that, we should be well positioned to be the technology of choice in virtually all power electronic applications. To get there, it took quite a bit of work. Over the last 7 years, we've put tremendous intellectual energy and financial resources into making this what we call the process design kit, or PDK. This is perhaps our most valuable piece of intellectual property. It's actually a trade secret because very few people have access to it. Even our suppliers do not have access to this. It's completely owned by Navitas. And you might think that GAN integration is an obvious or maybe even trivial thing to do. But the fact is that GAN is very difficult to integrate solutions into. You don't have a lot of components that are in the kit of the silicon designer. You don't have p-n junction diodes. You don't have bipolar transistors. You don't even have p-channel FETs. What you have are GAN transistors and passives. And what we've done is we've made a library of enhancement mode and depletion mode transistors across a range of power and voltage, as well as high precision and standard passive components, and that's what we use to develop our circuits. From that, we've developed innovative ways of making standard cell circuits, such as gates, comparators, charge pumps, level shifters, regulators, and the like. Many, many circuits that we've been able to put together in GAN that give us the ability to integrate all the necessary functions. Combined with that, we've got a very sophisticated characterization capability with real expert device engineers going down into all the levels of device behavior and building models that are highly accurate so that we can simulate our full circuit solutions very well and achieve first pass success with our designs. We even have a software that will take the layout of the circuit and extract every little parasitic of capacitance and resistance and inductance on that circuit and include that in the model. Having done that, we have developed these circuits and innovations with over 120 patents. They cover the area of devices, circuits, systems, and applications, as well as packaging. So we have a really strong patent portfolio in several countries around the world, heavily in the US, but also in Asia, and they cover the broad range of applications that we're talking about today. Our manufacturing process, as advanced the GAN technology is today, can fortunately be built with mostly existing manufacturing infrastructure. So we start with the silicon wafer. Obviously, this is a quite available commodity. We then grow a GAN epi layer. This is done with MOCVD tools that can grow that layer very effectively from several well-known suppliers. We then go to a silicon CMOS fab that is a 6-inch fab. It's not an advanced lithographic node. It's standard equipment, 0.35 micron equipment. So we can take good advantage of older and very cost-effective CMOS facilities. And then we go with customized packages, but using a standard manufacturing assembly process flow at well-known manufacturers, world-leading OSATs, offshore assembly test manufacturers. And they have capacity that's in the billions of units on a yearly basis. So we definitely have the ability to expand. And expand we need to do, because GaN is an expansive market opportunity. You can see here in a graphic that shows the power and the voltage of the domain of power electronics that GaN covers the majority of that range. We can operate from tens of watts to tens of kilowatts, and we can operate from less than 100 volts up to nearly 1,000 volts. And many, many applications fall within that domain. It's a $13 billion market opportunity and growing very rapidly. You can see some of those applications, and we'll discuss them in more detail. We've divided the chart between silicon, GaN, and silicon carbide. At the low voltage and low power end is silicon. At the very high voltage and very high power end is silicon carbide. And in the middle is GaN, covering a wide swath of applications. Contrasting GaN versus silicon carbide, this is always, or very frequently, a question. Both are compound semiconductors. Both are wide bandgap. So what's the difference? Well, GaN, Navitas GaN, is a lateral structure. That means the source and drain are both on the top of the chip, and the current flows laterally along the surface. With silicon carbide, electron flow is from top to bottom, from the top surface of the chip to the bottom of the chip. So that's very different. And that structure does not lend itself to integration of anything other than the power device. So it's very difficult to get drive and control or any other functionality on that chip. In addition to that, because of the lateral structure, GaN has an extremely high frequency capability. A very, very small percentage of the chip is actually consumed by the gate electrode. It's very tiny. So it has very low capacitance. It's very easy to get high frequencies. In fact, it's derived from RF devices that switch in the gigahertz range. So megahertz is so simple for GaN transistors. On the other hand, for silicon carbide, there's a lot of gate area and very much higher gate charge required to switch, so it's slower. In addition, silicon substrate, very low cost. Silicon carbide has to be built on a silicon carbide bulk crystal, so the cost of that crystal is about 10 times as high. It's very difficult to grow silicon carbide. You can only grow a crystal about that big, and it gets a few wafers out of each crystal. And they're very hard to machine. The cost is very high and will remain high. The one big thing silicon carbide has is the best thermal conductivity. For very, very high power applications like wind turbines, utility scale, and high power electric vehicles, silicon carbide will definitely be the choice for the future. So with that, I'd like to turn it over to Dave Carroll, our Senior Vice President of Sales, to discuss with you the market opportunities.
Great. Thank you very much, Dan, and good morning, everyone. So I'm going to talk about our first two focus market segments, starting with mobile devices. So we chose wall chargers for mobile devices because the value proposition is quite compelling and very simple, and the industry is quick to adopt new technologies. The trends in mobile devices are clear, with increasing screen sizes, more powerful batteries and processors, resulting in mobile devices that can take upwards of 3 to 4 hours for a complete charge. GaN ICs enable up to 3 times more power, meaning up to 3 times faster charging, in half the size and weight of traditional chargers. The market is actually huge, with 2.5 billion units shipped per year and over $1 of GaN content potential per unit. This represents over a $2.5 billion market opportunity. When you integrate multiple chargers into a single multi-port device, the value proposition becomes even more compelling. In this example, you can see 3 bulky silicon chargers being replaced by 1 multi-port GaN charger, which is 3 times smaller, lighter, and less expensive than the chargers it's replacing. When we launched our first GaN IC in late 2018, we saw aggressive, fast-moving aftermarket customers launching products into the market very quickly. By 2019, we'd launched dozens of new products together with aftermarket leaders, including Amazon, Baseus, Aukey, Belkin, Anker, and others. This trend has now migrated beyond the aftermarket into Tier 1s. In 2020, we began seeing Tier 1 OEMs launching GAN chargers, some of which were in-box models, meaning the charger would ship inside the box with the mobile device. Today, we have Tier 1 customers which include Lenovo, Dell, LG, Navitas, OPPO, and others. As mentioned earlier, we now have over 135 GAN chargers in mass production. You'll see many of them in the demo a little bit later, and over 150 new GAN chargers in development, targeting mass production in the coming 18 months. While we don't talk about unannounced products, we can tell you we're working with more than 90% of the mobile OEMs worldwide on next generation designs using Navitas GAN ICs. As mentioned, we've shipped over 20 million units without a single GAN-related field failure. This gives our Tier 1 customers high confidence in our reliability as we work together on next generation designs. So we have over 135 GAN chargers in production today. Based on our own research using publicly available information, we believe this to be more than all other GAN companies combined. While we do compete with other E-mode as well as D-mode GAN players, our primary competition continues to be silicon. In the chart on the right, you can see new mobile device platforms which have been announced by leading OEMs. You can see the power consumption is upwards of 100 watts. And there's more than, actually 10 of them have been announced using GAN, and 8 of those 10 are actually using Navitas ICs. As we continue to drive to cost parity with silicon in the coming 24 months, combined with our high reliability, we're paving the way for all mobile chargers to migrate from silicon to GAN. Beyond the mobile segment, we're also focusing on the non-mobile segments within consumer electronics, specifically focusing on devices that need higher power in smaller and slimmer sizes. These are products like ultra-thin LED TVs, gaming consoles, all-in-one PCs, and internet-connected smart home devices. GAN ICs make this power density possible, up to 3 times higher power density in the same or even smaller form factors. We've confirmed our lead customers in these segments today, including a Tier 1 LED TV, which is set to launch later this year, as well as a Tier 1 all-in-one PC, which will also launch later this year. Together, these two designs represent millions of devices, millions of units in 2022. Across these applications, there's more than 600 million systems shipping each year. With more than $3 of potential GAN content per system, this represents another $2 billion per year annual market. And with that, I'm going to hand it back to Gene to talk about our high power focused market segments.
Awesome. Thank you. I'll take this one. Thank you. Thanks, Dave. Fantastic. So Dave just outlined mobile chargers, consumer adapters, each a $2 billion market opportunity. Incredible market. We're just getting started, but we're not stopping there. In fact, we're excited about the SPAC IPO and the capital raise primarily to take that capital. 1, to accelerate the market opportunity Dave just outlined, but 2, to reach the full GAN potential in high power markets. We estimate across the 5 markets we're targeting that silicon today, or last year, is about a $9 billion opportunity. GAN is still very early days, 20 million or so in GAN revenues. That $9 billion in silicon will grow in total to about $13 billion, a nice sized market opportunity. Third-party estimates are that GAN will be about $2 billion of that. That's a doubling of GAN revenue for our industry over the next 5 years. That's a heck of an opportunity, and we plan to be the leader today and in the future. But keep in mind that $2 billion is only 15 or 16% of the real potential, $13 billion, again, across the 5 segments we're really targeting. Mobile and consumer are going to be a big piece of it, and I think these TAM estimates here are pretty conservative compared to the $2 billion each potential that we outlined. But I'd like to walk through the three others: data center, solar, and EV, which will add significantly to our revenue opportunity and drive a lot of our $2 billion penetration over the next few years. So let's take them one by one. Data centers is famously a big power problem. Almost half the cost of operating a data center is related to power. Cost of the power supply, cost of the electricity, cost of cooling. These are big numbers. By our estimates, a silicon-based data center is only about 75% efficient. That means of all the electricity going into that data center, 25% is wasted. It's burned up as heat. And that heat needs cooling, which is why cooling is another big problem. We predict that a GaN-based data center can jump that by 10 points. Those are big numbers, from 75% to 84%. When we do that and the world deploys GaN-based data centers, our estimates are up to $2 billion of electricity savings every year across those data centers. And that's not counting the cost of cooling and ultimately the cost of power supplies getting cheaper using GaN. But it doesn't stop there. We also shrink the size of the power supplies. You may not think the footprint matters, but it really does. This thing is filled with racks and racks and racks of data processors. But a third of those racks on average is filled with power processing, the power supply. We can shrink that down. And if we can cut that in half to 15% of the racks, more of the rack, more of the footprint goes to data processing, which is in the end what we want from a data center. These are big, big impacts. In total, we think this is about $1 billion opportunity. We've already engaged the lead customers. A lot of these lead customers are the same ones we're selling to for consumer adapters, so it will be a very fast adoption. We're developing the leading products this year to introduce to those customers later this year, and that revenue ramp will start in data centers for us late next year. Cryptocurrency mining, by the way, with all of its ups and downs, I think it's here to stay. I think long-term it's going to be a big market, and it is a monster power hog, almost identical in power electronics challenge and opportunity, and another perfect fit for GaN. That $1 billion estimate I give does not include cryptocurrency mining, but that's definitely going to be an additional upside market we will pursue. Second one is solar. GaN fits like a glove for solar. If you really boil it down, it's just dollars per watt. What do I have to pay in the upfront hardware to install solar, and then how much free energy or free watts am I going to get instead of pulling it from the grid, pulling it from my solar panels? Now, we can't help them. We're not used in the panel, but the second biggest power problem, if you will, or opportunity and cost is in the inverter. The inverter is just the name of the solar power supply. Over the next few years, we'll cut the cost of those solar inverters by 25% while improving the energy savings by 40%. So we're cutting the upfront solar installation costs while maximizing those free energy, free watts over time. By our estimates, we think that's going to improve the solar payback by about 10%. This is already a market accelerating, growing extremely fast, and we're going to add to that acceleration while displace silicon and move it over to GaN over the next few years. Here again, we've engaged our first lead customers. We have one of the top solar residential players in the world. We'll be changing from silicon to GaN in the next 2 years. This is a big commitment, a big decision. Navitas is the leading supplier, GaN supplier, to make that happen. This program alone, we estimate to be $500 million in revenue potential for Navitas over its lifetime when it goes into production starting in 2023. Big opportunity, and here again, we estimate the total market to be about $1 billion. And a similar timeline as data centers, we're developing the prototypes now. Those samples will be delivered late this year, and then the customer will do their field testing and start ramping in 23. Third and finally, and probably the biggest, longer-term market, but the biggest market, electric vehicles. Super exciting opportunity filled with power electronics inside that car. If you look at the car picture, I'm highlighting 3 main applications. The onboard charger, just like fast charging a 20-watt phone, we're going to fast charge a 20,000-watt onboard charger. That gets that power onto the high-voltage battery. The DC to DC converts the power from the 400-volt battery down to the low-voltage battery and powers the rest of the electronics. Third big application, traction drive, the actual electric motor itself. All 3 of these are great opportunities for Navitas. Our first lead customer is lined up. It's an onboard charger customer for one of the top European car companies in the world. They, as well, will be switching from silicon to GaN for their next generation onboard charger. We are enabling them to triple the power handling of that onboard charger. That's 3 times faster charging. Most OBCs today are about 6 to 7 kilowatts. The one we're designing, and we're going to show you an early prototype later, will be 20,000 watts in the same size and weight or less than the one today. That's some pretty exciting stuff for the consumer. It's at least $50 of GaN content for Navitas. Spread that over 50 million cars a year. The OBC opportunity alone is a $2.5 billion opportunity. On top of that is the DC to DC potential, and then the traction control or electric motor. Big potentials here. The bar charts I shows actually come from our lead customer telling us all the benefits when we apply silicon to GaN across these 3 applications. Not just the fast charging for the OBC, but when we cut the power dissipation, in other words, improve the energy savings across all 3 of those power applications, they estimate that they can cut $500 out of the battery cost for the same driving range. $500 is something a car company would kill for as they're trying to cut the cost of EV premiums back down to the price or lower than gas cars. Or conversely, for the same battery size, we can extend that range by 5% or more. Every single point is a really big deal in the future of EV and accelerating the adoption of EV. A lot of financial opportunities, a lot of market opportunities, but I want to come back to the point I raised at the beginning. This is also a huge opportunity to help our climate. We are serious about net zero, the Paris Accord goal to get to net zero. Our customers are very serious about it. Today, as a planet, we emit 30 to 35 gigatons of CO2. By some party estimates, IRENA estimates we have a 26 gigaton gap. With everything countries and companies have done so far, they're estimating maybe we're cutting that 5 or 10 gigatons. We got a long way to go. 26 gigatons. By Navitas experts, and we've actually hired third parties to come in and really help us to predict and set up metrics and estimate what is the CO2 impact. As I said earlier, every single GaN chip we sell is energy savings to our customers. Less energy is less CO2. Our estimates are we can impact about 10% of that gap, 2.6 gigatons a year. Those are big numbers. We're excited about that for Navitas. We're especially excited for our customers. We're now engaging our customers at a corporate level like Dell, Google, who are realizing the faster they adopt GaN, the faster they achieve their own net zero initiatives. That's a great corporate resonance and sort of accelerant on top of all the other good reasons to adopt GaN. All right, so let's turn now to the financials. How does this all roll up together? Last year we did 12 million. This year 27, nearly all mobile-based, of course. We've got some consumer kicking in a little bit in 22 and ramping in 23, but then we see data center and solar kicking in significantly, as I outlined, in 23 and 24, electric vehicles starting in 24 and 25. When you add it up, we're nearly doubling every year, ramping to 640 million, which we view as a conservative view of about 30% of that $2 billion opportunity. And again, we're really eyeing the bigger $13 billion opportunity and driving that $2 billion of GaN adoption faster and sooner. I didn't mention it before, Dan described the manufacturing another big benefit of GaN is you can use common silicon manufacturing tools. And we're using older tools. The world is clamoring for silicon capacity today, but they're fighting over 8-inch, 12-inch, advanced lithographies like FinFET. We are using 0.35 micron 6-inch. This is not in high demand like the other semiconductors. It gives us a great opportunity for upside. And we've already negotiated capacities that are 50 to 100% greater than this revenue forecast. So while the world is struggling with 6-month allocations and long lead times, we are offering 6 to 12-week lead times and 50 to 100% upsides to our customers. In addition, visibility. I mentioned earlier, $680 million pipeline. I want to break that down a little bit. We put it as awarded and qualified. Awarded is production programs that are committed to use GaN or committed to ramp with production Navitas GaN quite soon. That's very high confidence. That's $100 million of that $680 million. That $100 million then gives me great visibility and confidence over to the 27 today and the 69 million next year. But we have 580 million of qualified opportunities on top of that. That includes a lot of upsides with chargers and adapters that can give us upsides this year and next year, but it also includes those early programs I described in our expansion markets, solar, data center, and EV. With that, I'm going to introduce our head of finance, Todd Glickman, to talk about our short-term and a long-term operating model. So all you.
Thanks, Gene. All right, so along with growing revenue, we are going to aggressively grow our gross margins as well. As you're seeing here, we finished the year 2020 with a 31% gross margin. We quickly changed from Gen 1 to Gen 2, driving margins to 46%. Q1 came in at 44%, and we're still on track to achieve the 46% by the end of 2021. But 21 is only the first step in our revenue, in our gross margin ramp. From 21 to 26, we're going to grow gross margins by 4 focus areas. First, new generations of technology. Every 12 months, we're going to come out with a new generation of technology that's going to drive cost from 20% generation on generation reductions, with the majority of that cost moving to our customers. Because our ultimate goal is to drive that GaN premium to 0, and this is how we're going to do it. Secondly, integration. Right now we integrate drive, control, and protection, but we're just scratching the surface. With every new generation that comes out, we're going to add something else in there that's going to continue to drive more integration and simplify the GaN adoption. Thirdly, optimize our supply chain. As we enter new markets, we want to continue to optimize our supply chain. And lastly, as revenues increases, we're going to drive our cost of materials lower, passing along some of that to our customers, but keeping some of it to increase our margins. Now, all this allows us to achieve that 55%. However, we believe that there's upside to go to 60% long term, but our primary focus today is to concentrate on revenues and then long-term focus on margins once we have moved the majority of the market from silicon to GaN. So then if we look in the upper left-hand corner, let's focus on EBITDA. So today we have a negative EBITDA, but we plan to pass into a positive territory in 23 and move to a healthy margin of 25% by 2026, with the majority of our costs in 26 still focused on R&D. Now we can do all this with basically 0 CapEx. Today our fabless model is very lean and allows us to maintain 0 capital expenditures. But long-term, all this CapEx growth is going to be concentrated towards limited testing and manufacturing equipment, but always be maintaining less than 5% of our revenues, which allows us to maintain our identity as a fabless semiconductor company. So with that, I'm going to hand it over to our business partner, Gary from Live Oak, to discuss the business combination.
Thanks, Todd. Just a quick overview of the transaction. The total purchase price is $950 million. It's about a little over 5 times 2023 revenue. It's funded by a fully committed $145 million PIPE and $253 million in trust of Live Oak Acquisition Corp. 2, it's LOKB. A couple of things we wanted to point out is 100% of the existing Navitas shareholders are rolling into the transaction, which includes Capricorn and Atlantic Bridge. The Live Oak sponsorship is putting 20% of the founders' economics into an earnout at $12, $17, $12.50, $17, and $20 a share, along the same lines as a 10 million share earnout that's going to the existing shareholder base. Additionally, we put some more restrictions around the founders' economics and restricting the stock for up to 3 years, 1, 2, and 3 years, which also aligns ourselves with management teams. The management will also be subject to the same lockup. What we hope this reflects is our true excitement about the long-term prospects of Navitas. We're really excited about being a shareholder here and partnering with Gene and this world-class management team. Pro forma valuation is just over $1 billion, which represents a 5.7 times 2023 estimated revenue of around $182 million. I also want to stress it's 2023 revenue, and we have an inordinate amount of visibility into that number and a high degree of confidence that Gene will meet or beat that number. From a valuation perspective, our trading multiples, we based on a power semiconductor comps 9 to 13 times 2022 estimates. And what we did is we took our 2023 revenue number, used the 9 to 13 times of the 2022 estimates, and discounted that back to 20%, which should show you a 60 to 90% upside case from a valuation perspective. And with that, I think I'll turn it back over to Steve, who will go through some of the milestones and highlights coming up. Thanks.
Thank you, Gary. Thank you, Gary. So to wrap up the main presentation, as you can see, we've got an intense series of events coming up in different locations. I'm very happy to see you guys here in person and online today. We hope to continue that as much as we can. We feel that we have some excellent demonstrations that only kind of an in-person you can really get the benefit of those demonstrations. So as you can see, we've got a range of things coming through. We've got technology with Dan as a CTO. We've got the green element with net zero coming up as well. So a lot of different things for us to do.